Hi, today I'll be presenting some work on the local tree width of random graphs with applications to stopping contagion in networks. I'm Hermish, and this is joint work with Daniel Reichman at WPI. First, let me start by laying some groundwork by introducing the concept of tree width and random graph models. So a tree decomposition of a graph G is a tree on subsets of its vertices that satisfy a few key properties. On this slide, you'll see an example of a tree decomposition. Notice the vertices of T, which we call bags, are subsets of the vertices of G. For a tree decomposition to be valid, every vertex of G must appear in some bag of T. In addition, every edge in G must have some bag in T that contains both endpoints. And finally, each vertex in G must correspond to a subtree of T. So to make the last thing a little bit more concrete, consider the vertex B in G. Now, if we look at all bags in T which contain B, we see that there's exactly 3 of them, and they form a subtree of T. This last condition is equivalent to saying that if both xi and xj, 2 bags in T, contain some vertex, every bag on the path from xi to xj contains that vertex as well. And since it's a tree, this path from xi to xj is unique. Okay. So in the tree decomposition that we saw previously, you'll notice that the size of each bag was 2. In this case, we'd say the width of that particular tree decomposition is 1. It's always 1 less than the cardinality of the largest bag. The tree width of a graph is the minimum width among all possible tree decompositions of that graph G. So the particular graph that we saw, which in fact was a tree itself, its tree width was 1. We found a tree decomposition with bags of size 2. But if we take a slightly more connected graph, for example, the complete graph on 3 vertices, you'll find quickly that it's impossible to come up with a tree decomposition whose bags all have size 2. You'll find that you need a bag that contains A, B, and C, and therefore its tree width is at least 2. In fact, its tree is exactly 2. So already you can sort of see more simple tree-like, less connected graphs have lower tree widths than graphs that are more connected. And that intuition sort of that intuition sort of is true more generally. So what you'll notice is trees have tree width 1. We saw an example of this already. And in general, the complete graph on n vertices has tree width n minus 1. So this is on the order of n, roughly. It's linear in the number of vertices. Graphs that are somewhere in between these two extremes, like grid graphs, fall somewhere in between this sort of spectrum. So, grids obviously are cyclic. They have cycles, unlike trees. But on the other hand, they're not as connected as the clique. It turns out the tree width of an n by n grid is exactly n. So this is, its tree width is roughly on the order of square root of the number of vertices. So already it seems like, this notion of tree width is capturing how complex or how tree-like a graph is. So natural question is like, why does this matter? Why do we care about tree width? Well, it turns out for certain NP hard problems, like the maximum independent set problem, it's hard in general, but it also admits efficient polynomial time algorithms on trees. This is perhaps not too surprising because trees are extremely simple graphs. But intuitively, we might also expect similar results to hold for graphs which are not exactly trees, but are somewhat tree-like. We want to use, this new tree width definition that we have, maybe, graphs that have bounded or slow-growing tree width. And that in particular is true for the maximum independent set problem. For graphs with bounded tree width, you can find the maximum independent set in polynomial time. So let's now take a U-turn from talking about tree width to briefly talk about 2 random graph models we consider in our paper. The first is the classic binomial random graph. Here we have a random graph on n vertices, and we add each edge independently at random with probability p. We also consider the noisy tree. The noisy tree we get by starting with an n vertex tree, T, and adding each non-edge independently at random with probability 1 over n. So the resulting graph isn't a tree because the additional edges that we add introduce cycles, but it's sort of it is sort of tree-like in the sense that it's basically a tree. We just added a couple extra edges here and there. Okay, so the core motivating question of our work is, can we apply Treewidth techniques to solve algorithmic problems on random graphs? And at first glance, it seems like the answer to that question should probably be no. The binomial random graph has been well studied, and one thing we know for sure is that under the supercritical regime, where p is greater than or equal to 1 plus delta over n, G and P has Treewidth linear in n. This is sort of a worst case Treewidth that puts it alongside the complete graph. Remember, the complete graph also has linear Treewidth in the number of vertices. And so it might appear like, hey, there's nothing to do here. But on the other hand, there's this other observation that despite having high global Treewidth, locally the random graphs are pretty simple. They're almost tree-like with high probability. To make this a little bit more concrete, you can say a ball of radius O of log sub d of n around every vertex is roughly a tree plus a constant number of edges. And so this observation sort of motivates our definition of local Treewidth. The local Treewidth of a graph, denoted T sub k of G, is the largest Treewidth of any size k subgraph of G. We might hope that even though a graph has high global Treewidth, in absolute terms, if you start looking at sort of subgraphs of size k, it may have low local Treewidth. And maybe this local Treewidth can then be exploited to devise efficient algorithms. Okay, so now we highlight some local Treewidth bounds for random graphs. First, we have the following upper and lower bounds for the binomial random graph. So you'll notice here that we show that the Treewidth of G and P is bounded from above by 3 plus big O of k log d over log n. This is exciting because it's sublinear in k. There's this log n factor in the denominator. On the other hand, our lower bound is pretty close. It says the local Treewidth of order k of G is at least big theta of k over log n. So this is almost tight. We've almost pinned down exactly the binomial random graph's local Treewidth up to this factor of log d that's present in the upper, but not the lower bound. We also have a similar kind of result for noisy trees. You can show that if we start, with some tree, some n vertex tree with maximum degree delta, and then we consider the noisy tree that we get from it, with high probability, the noisy tree's local Treewidth of order k is bounded by 3 plus big O of k log k plus k log delta over log n. So this is sort of similar, except now there's this k log k factor, and there's also this dependence on the maximum degree of the tree we started with, k log delta. Okay, so let's now dive into the techniques we use to establish these bounds. So in this talk, I'll focus primarily on the GNP case for simplicity, but it should give you a flavor of the types of arguments we use in our paper. The big idea for the binomial graph upper bound proof is to rely on the edge excess principle. In other words, we show that the subgraphs of size k of GNP can contain too many edges, and therefore can't have too large a Treewidth. To make this argument more formal, we prove the following proposition. Say G is a connected graph with n vertices and n minus 2 plus L edges. Then its Treewidth is at most L. We prove this by taking a spanning tree of G. This spanning tree has n minus 1 edges, but only has Treewidth 1, because it's a tree. To get from the spanning tree to G, we need to add exactly n minus 1 additional edges. And each edge can increase the Treewidth by at most 1. So the resulting graph G, therefore, has at most 1 plus L minus 1, which is the same as L, Treewidth. This completes our proof. So now we're ready to prove our main result. To bound the local Treewidth of G and P, we want to show that the probability that some subgraph of size k has large Treewidth, let's say, greater than some r, is small. But any graph with large Treewidth has a connected subgraph with the same Treewidth, right? You just prune off some parts of the subgraph, of the graph. So Instead, we can choose to bound the probability that some subgraph on S less than or equal to K vertices is both connected and has tree width greater than R in G. Okay, so now let's fix some subset of S vertices in V and ask what the probability is that the resulting subgraph in G will both be connected and have tree width greater than R. So computing this probability exactly is a little difficult, but we can upper bound it by using the proposition we have earlier. So first, we're going to count the total number of spanning trees on S vertices because we want to check that it's, we want to make sure it's connected. And then to ensure, because it has tree width greater than R, we know that we must have at least R additional edges. And so then we count the total number of ways to choose R additional edges. And then we multiply that by the probability that all R plus S minus 1 edges occur in the graph. But this argument, it just tells us whether or not a single subgraph is connected and has tree width greater than R. To actually bound the probability that no such that any such subset exists, we need to take a union bound over all n choose R possible subsets, letting S range from 1 to K. And now what we found is by taking R to be some constant plus K log D over log N, you can force this probability to be at most 1 over K, after which the statement follows by a simple union bound over all Ks we're interested in. So that summarizes the upper bound proof for the binomial graph. The lower bound proof, on the other hand, is a bit different. So to show that the lower bound of G and P is at least big omega of K over log N, we use the following approach. So first, assume I can find some graph H with S vertices, S edges, and tree width big omega of S. Then assume furthermore that I can find an embedding of H with width log N in G, let's call it H prime. This subgraph H prime of G has S log N vertices because it's an embedding of H with width log N, and it has tree width of big omega of S. This is because H is a minor of H prime, and therefore the tree width of H lower bounds the tree width of H prime. So, so now we have some subgraph of G whose width is, let's call, K to be this big O of S log N, and it has tree width K over log N. So all that's required to sort of complete this proof is to show one, we can find, such graphs H. And then for these particular graphs, there always exists some embedding into G and P with width log N. So first we get, this first component we get by looking at random through regular graphs. And the second bit we sort of, it follows from a result of Krivlevich. And this basically completes the proof. Okay, so now let's explore how these local tree width bounds can be applied to derive more efficient algorithms. So to do that, we sort of introduced the minimizing contagion problem. But before I do that, I need to talk about the R-neighbor bootstrap percolation model. So in R-neighbor bootstrap percolation, we start in a graph with some initial set, let's say A sub 0 of infected vertices. Then at each step, a vertex also gets infected if at least R of its neighbors are infected or activated itself. So you can sort of see an example of this process mechanically at the bottom of this slide. We start with some original seed set, A sub 0 of 2 vertices. These 2 vertices then on the next step infect their, they infect their shared neighbor. And now the shared neighbor plus one of the original vertices on the next step infects one more vertex. At this point, no matter how many additional steps we run the process for, no additional vertices will be infected. Everything is infected except for one vertex, and that one vertex has a single neighbor, so it's never going to get infected. But in general, this process can be quite complex, and it's controlled by a number of different factors here. Okay, so given a contagious process that evolves via R-neighbor bootstrap percolation, we now introduce the minimizing contagion problem. We're given a graph, we're given a seed set A from which the infection starts, and a parameter S. we want to figure out what the minimum number of edge deletions required to ensure at most S vertices in V minus A are infected. So you can imagine an extreme case where we just cut all the edges to isolate A. In that case, there will be no additional, no additional infections in my graph. But here the goal is to delete as few edges as possible while ensuring that too many infections don't occur in the rest of the graph. Given the combinatorial nature of this problem, you might not be surprised to find that this problem is actually NP hard. You can prove this result via reduction from vertex cover if you set up the right gadgets here. So given this NP hard problem, a reasonable question is, why should we care about minimizing contagion at all? And the answer is, in the context of the COVID pandemic, it's perhaps not too surprising why this problem might be interesting. In this setting, edge removal from networks, in the context of some pandemic, could be viewed as necessary social distancing measures to prevent spread. In the real world, we might want to control spread while simultaneously minimizing disruption by deleting as few edges as possible. So an example, that often pops up is if you have some model of railways and air routes, edge deletion here might correspond to shutting down those routes. And so you might want to minimize edge deletion to prevent disruption, while also achieving whatever target goal that you have. Okay, now let's see how these local Treewidth bounds lead to more interesting algorithms, more efficient algorithms for the minimizing contagion problem. The algorithms we sort of work with rely on three sort of things being true, three observations or conditions. One is we want to make sure that we have the bounded spread property. This says that the set of seeds A does not infect too many vertices. This bounded spread property allows us to solve the minimizing contagion problem on some small subgraph rather than the graph as a whole. We can then apply some local Treewidth bounds to then say this small subgraph that we're solving this problem on also has low Treewidth. If these are true, then we can just apply a fast algorithm for minimizing contagion on graphs of bounded Treewidth. So we've talked a lot about bounding local Treewidth already, and you'll soon see some examples of bounding spread or showing the bounded spread property holds. So I just want to take a second to demonstrate that there do exist fast algorithms for minimizing contagion in graphs of bounded Treewidth. In fact, we provide an example of one in our paper. At a high level, it's a dynamic programming algorithm that solves a slightly more general version of the infusion-diffusion minimization problem that's been studied before. It essentially works by solving some version of the minimizing contagion problem on subgraphs of G and then carefully combining them by accounting for interactions of the percolation process between subgraphs. So it sort of follows a common theme in these bounded Treewidth algorithms, which is that you sort of you have some dynamic programming algorithm that basically solves some version of the problem on subgraphs of G that correspond to subtrees of the rooted tree decomposition. We then sort of start at the bottom and we cleverly combine solutions to subproblems until we get the result that we want. More information about this is found in our full paper. Okay, so let's see all of these things sort of come together. And a grid graph, and the grid graph is a good way where all of this sort of comes, where you can sort of see all of this come together. So first we show that the bounded spread property holds for grids. So in the n by n grid, you can show that every set of size k infects no more than O of k squared vertices, assuming R is at least 2. The way we prove this is by taking the grid and embedding it, taking the graph and embedding it onto a grid, coloring in sort of the squares that correspond to infected vertices. Here you can sort of see two examples of two sort of two infected vertices close by infecting one of their shared neighbors. What you'll notice is that the perimeter of the infected region is not increasing. You can prove this is true in general, which means that from our set of size k, which has perimeter at most 4k, the infected set that we get also has perimeter of size at most 4k. This accommodates at most O of k squared infected vertices, which concludes our proof. Notice that this bounded spread property immediately gives us a 2 to the power of O of k squared poly-n algorithm. We know to restrict ourselves to this, subgraph of size k squared, you can sort of, guess solutions, or you can sort of brute force the solution optimally by just guessing edges. We show now how we can actually improve upon this result by taking advantage of bounded local Treewidth. So to do that, we need some bounded local Treewidth resolve, and that comes fairly easily. If I have some subgraph of the n by n grid with r vertices, we know it has Treewidth at most O of square root of r. This simply follows from the fact that the grid graph is planar, and every m vertex planar graph has Treewidth O of square root of m. Okay, so now let's put all of these pieces together. And let's say we have an n by n grid and we have some initial seed set of size k. Because we know that from the bounded spread property, we only need to consider the subgraph of G that correspond to all potential infections, which has size at most k squared. We know this subgraph has Treewidth big O, O of k. So now we can just apply our bounded Treewidth algorithm to this subgraph that has Treewidth O of k. And we'll get an algorithm that runs in time 2 to the power of O of k poly n. This is an improvement over our original naive algorithm of 2 to the power of O of k squared poly n. This is because we're sort of exploiting the fact that the subgraphs that we're looking at actually have low Treewidth. Okay, so now let's sort of apply, the grid graph sort of highlighted our algorithmic approach. Let's apply a similar process to get algorithms for minimizing contagion on random graphs. In particular, we show the following result for GNP. So recall, for the binomial random graph, we already established an upper bound of the local Treewidth. And I already have mentioned that we have a fast algorithm for minimizing contagion on graphs with bounded Treewidth. So the only piece that's sort of missing here is the bounded spread property. And it turns out that you can show for any set A that's not too large, this set A will not infect more than size of A times log D vertices. So some version of a bounded spread condition actually does hold here as well. So putting all of these together, we can get the desired result in sort of the following steps. So first, remember, we have some set A of size k, and now we consider bracket A, which is the set of all possible infections from A. We've shown from the bounded spread property that this set has size at most O of log D times the size of A. Furthermore, our local Treewidth bounds tell us that this subgraph has bounded Treewidth. We know its Treewidth is at most, its size times some constant plus its size times some constant factor times log D over log n. So we have a relatively small subgraph in terms of size, and we know it has bounded Treewidth. That means we can apply our fast algorithm that solves minimizing contagion for graphs with bounded Treewidth. There's one more complication here, which is that algorithm's running time actually depends on the maximum degree of the graph. But since we're working with GNP, we know that with high probability that the maximum degree is big O of log n over log n. So we can now sub that in, and we can actually get the result that we desire, which is that you get an algorithm that runs in exponential time in O of k log squared D log n over log n times poly n. So with that, I just sort of want to wrap up and talk about some future directions for our research. So first, we're really interested in seeing if our results can be extended to directed graphs and weighted graphs. This might be more realistic in terms of actually modeling epidemic spread. We also want to see, we focused a lot on solving this problem exactly. How well can you approximate this problem, perhaps on planar graphs? And then sort of more specifically, we have these upper and lower bounds for the local tree width of G and P. We want to understand, currently they differ by this factor of log D. Can the lower bound here be strengthened? Can we make this tight? Can we get rid of the missing log D factor on our lower bound? And finally, for this noisy tree setting, we found that our upper bound depends on the maximum degree of the tree that we started with. And that's a little unpleasant. So we're wondering if it's possible to sort of get rid of that dependence on the maximum degree. So these are all, I think, exciting future directions for work, and we look forward to sort of working on these in the near future. So with that, I sort of want to thumb through the references. Our work was inspired by a lot of the work here and builds on it. So just wanted to quickly run through this, and I'm really looking forward to seeing everyone at Random. Thank you.